I'm glad you reminded me of the title because I had forgotten what I was supposed to be talking about. My talk that I put together, I got about 40 slides, 38 slides, something like that. Actually does have a lot of emphasis on light absorption by aerosol. So that's good. But it's not only that. Um, it's really more about air pollution broadly. So let me go ahead and get going here. And I think if I put it, let's see, if I put it in slideshow mode, are you able to still see it correctly? Okay, cool. So I'm what's called an atmospheric chemist. I am really a chemist. So thank you for letting me join the physics gang for a day. Pretend that I'm a physicist, but of course, chemistry and physics have a huge amount of overlap, and we often forget, that things that we're teaching. We teach spectroscopy a lot in chemistry. Well, that's done in physics as well, and quant mech. Well, we do that in chemistry as well as in physics. So there's a lot of overlap in the topics. Interestingly, though, they're often taught differently. Our absorption cross sections are often in different units from the ones I see a physics faculty using. Okay, it's just different units. We're really talking about the same thing. Now, as an atmospheric chemist, I say chemist, I could also say atmospheric physicist. Um, my interest is in air pollution and what we breathe. And it just doesn't matter to me whether it's really all about the chemistry or the physics. You really have to understand some of both of those. That's a picture of Seattle downtown Seattle from the Space Needle. If you're not from the area, then you might recognize that's Mount Rainier out there in the distance at 14,000 feet or 4.5 kilometers. Um, and this is from the Space Needle, so looking south, and the sun is setting off in the west. And we'll come back to that picture a little later with a different view, but I wanted to start with that one. So this is sort of more of a research presentation. It's not a talk that I would give to a class or parts of it, but it's really about the work that my team is doing. And so start out with what do we try to understand? So our mission, the way I've framed our research team, is to study and understand sources of air pollution, particularly in the Arctic and the Western United States, and the pollutants defined by the chemistry, ozone, aerosols, and mercury, the ones that we've spent most of our time worrying about, and trying to understand where they come from, the chemistry of them, and the physics of them, and how they link to climate change. And also, I should put on their human health, because that's really often a driver for all of this. So it tries to give you a little bit of scope of what we seek to study. And as you can see, I don't have a whole lot of hair left these days. I've been doing this for a long time, like 30 years as a professor. And I've had the fortune to be able to do this pretty much all over the world. And so one way or the other, we have made measurements of chemicals, gases, and aerosols, all those places. So it's kind of cool, the opportunity. And also you see, we've been on a number of different aircraft campaigns. And now I'll talk a little bit about the research station that we have down in Oregon at 9,000 feet. Mountains are really interesting to me. I like them, and I'm really attracted to them. And so I put a research station on the top of that mountain down in Mount Bachelor, which is at 9,000 feet. And it's a very unique station. And I've managed to keep it running mostly with funding from the National Science Foundation since 2004. So I guess we're going on almost 17 years operating that site down there. Give you an idea of what we're doing right now. Sort of some of the biggest things that have going in my lab is trying to understand global, regional, local sources of ozone and PM. PM is particulate matter aerosols. You're going to learn a lot more about PM if you don't know much about that now. Wildfires, those have become a huge issue, especially out here in the West. And so we have a lot of interest in what's happening with the smoke and what are the impacts of it. So we have a number of projects focused around understanding PM and ozone from wildfires. And then we're also looking GC on the last one, GC mass spec, GCMS is method, chemical instrument to measure organics particularly. And we're using that to look at benzene and other toxics in the air, both from wildfires as well as from gasoline emissions. So those are some of the biggest foci in my lab right now. And I always want to remember to acknowledge the people in my team. This is, science is not an individual sport. And I always I always think it's funny how movies portray scientists. You know, we're always up in our labs. It's usually in the basement or in the top floor, and we're always alone. Usually it's a guy, and we're always alone tinkering with the instruments late at night. Well, that is not how it works because it is not an individual thing. It is always done in teams. And all of the work that we've done, is done, and all of the papers that we've published are always done in collaboration with everybody in the group. So Colleen and Ruby, who were former undergraduates, got their degrees at UW Bothell. Deanne, who's a sort of a admin assistant. Nate Ninneman, who's a postdoc, and Nate May, who's a postdoc, and then Noah, who's a technician for the site up at Mount Bachelor. And then, of course, we have to pay for this stuff. So yeah, as a professor, one of the things we have to get good at is writing grant proposals, and that pays for all the bills. I'll talk a little bit more about this. I'll show you some of the data we have from Mount Bachelor. And it's been a really cool site for us. I didn't start working there. We actually did aircraft studies off the coast of Washington. We had a site up here at the tip of Washington State called up by Nia Bay. But one of the things we really got interested in is understanding the atmosphere above the boundary, above the ground level. And so finding a mountain where we could do this. Now, Washington has lots of mountains. This turns out to be a long ways away, and it's kind of a pain to get down there. But it turns out that we needed a mountain, first of all, an isolated mountain. So a volcano is perfect all by itself. We needed power and we needed access. Well, that's a tough bill to put together if you're trying to find a mountain. So I was able to find this location. That's a ski area. You can see all the ski lifts, all the ski runs here. And there's actually a ski lift that runs right to the summit of Mount Bachelor. And we've operated a research station there since 2004 in collaboration with the mountain, obviously, with the cooperation of the ski area and with funding from the National Science Foundation. It's been a super successful research effort that we've done over the last, going on 20 years now. Now, let's talk about air. That's what I studied. What is air? Is air only gas phase molecules? Well, we got nitrogen, we got oxygen, argon, carbon dioxide, neon, helium, and then we got all the trace pollutants that are the things we most worry about. Anybody want to answer that question? Is air only gas phase? Okay, no. We got clouds, we got ice. You know that clouds can be both liquid and solid. You can have ice clouds and you can have liquid clouds. Can you tell the difference between the liquid and the solid clouds in those pictures? Well, I would guess these two in the middle are liquid droplets, and these cirrus clouds, these high elevation cirrus clouds, are almost certainly ice droplets. A lot of times the ice droplets, they evaporate more slowly. So every cloud is in a cycle, it forms, and then it goes somewhere drier and it evaporates. And only about 1 out of 10 clouds actually rains. So every cloud you see is in the process of either forming or evaporating, or maybe just floating by, but at some point it's going to evaporate. And ice clouds tend to evaporate very slowly. So they have very diffuse edges. And like you can see right out there, can you see the pointer, by the way? Yeah. So right out there in the edge of that cirrus cloud, you see it's really diffuse. That's because it's starting to evaporate, but it hasn't completely evaporated. And so it's just slower to evaporate than are the water clouds, which have much sharper edges. So that's how you can distinguish between an ice and a liquid cloud. Of course, we get this stuff like hail or sleet. And then what about this one? This is the famous London smog of 1952. So that stuff's in the air, and it's not natural. And so what we're seeing there is a mix of things like coal smoke in London in 1952 in a particularly bad air pollution incident, which killed several thousand people in London. But we're also seeing water vapor mixed in with coal smoke, and water vapor will actually glom onto those particles. So air is not just gas. There's all sorts of phases in it. From an air pollution point of view, excuse me, we're interested mostly in the gases and in the solids, the particulates, like that air pollution down there. So most of the talk, I'm going to talk about particulate. So I use this term particulate matter, PM. This is a diagram I swiped off the EPA website, which talks about different sizes of particles. So if you think about hair, yes, I do have some hair way back there. Hair like around 90 or 100 microns. Oh no, 50 to 70 microns. Beach sand is 90 microns. So these are relatively larger particulates, but the things that really matter are these fine particles. And usually we go by PM 2.5. That's actually the one that's the regulatory standard. And that means it's 2.5 micrometers or 2.5 microns in diameter. And you'll see in a minute, the importance of these is that we can inhale these and they get deep into our lungs. Whereas big dust particles or sand particles, first of all, sand is going to fall out very quickly. Dust particles are going to get trapped in our nose and not make it into our lungs. So the size of the particle makes a big difference, both in terms of the chemistry, the physics, and the human health impacts. So from a regulatory point of view, the PM 2.5 is the one that we're going to focus on mostly. So I mentioned the health impacts, and that's a big part of what we do, obviously. Different toxins and pollutants have different impacts. When we're talking about the particles, the solids and liquids, how far they get into our body really depends on their size, the particle size. So it's these very fine particles, less than 2 microns or so, that are really reaching our lungs and doing the most damage in our bodies, whereas the larger particles are getting trapped in our nasal cavities. And notice that our nasal cavity acts like is curved, and so there's an impaction that occurs for large particles as they come into our nose. Now, of course, I should have backed up a minute. Why do we care about PM? Well, there's 3 reasons we care about PM, really 2 reasons, but I'll say 3. PM, health effects. So we inhale them, that's not good. Cigarette smokers, anybody cigarette smokers on the call? Quit now. It's not good for you. You are inhaling a massive dose of particulate, carbon monoxide, benzene, and all sorts of things. So if you're a cigarette smoker, you can forget about air pollution because the levels that you're doing to your body already are much worse than anything you're getting from air pollution. But, clearly, as you inhale these things into your body, this is not good for your organs, for your heart, for your lungs. It turns out aerosols are also very important for climate. And these are different examples of aerosols. And I use this term particulate matter or aerosols. Aerosols is a suspension. And here we're seeing haze over Los Angeles, which is a mixture of both pollution from a lot of cars and industries, but also water vapor turns out to be important in that. Here we're seeing a dust storm. This is the coast of Africa. And we're seeing a dust storm that's coming out of the Sahara, the Sahara Desert. And here we see dust that's been deposited on a glacier. You can see how the glacier has been discolored, and that's going to affect the albedo, the light reflectivity on that. And here you can actually see a whole bunch of different things. These are off the coast of California, and there's a bunch of fires burning. And here you can see the smoke. And over land, the land is dark green, but the smoke is white. So that has an effect of reflecting more sunlight back into space. But then that smoke moves out over the ocean where it's cloudy here. And now the smoke is darker than the clouds. So here the smoke is increasing the solar absorption. And then to top it off, you have another effect going on in this picture. It's hard to read here, but these are ship tracks. And what's happening here is the aerosols from the stacks of the ship that are burning diesel or bunker fuel are actually seeding clouds under the right conditions. And so we're getting a cloud seeding experiment going on here. And those clouds are now reflecting more sunlight back into space. So this is a really complicated story. Do aerosols cool the planet or do they warm the planet? Whew. I mean, it depends on which aerosols we're talking about. These ones are probably having a cooling effect. These ones probably having a warming effect. These ones a cooling effect. These ones a warming effect. These ones are melting the snow more quickly. Wow, what a complicated story. And that's why one of the most important uncertainties in our understanding of global warming. And I'll talk about that in just a second. The last reason aerosols are important is visibility. And we like our vistas. And historically, as we've cleaned up pollution, we've done a lot better at being able, or we've cleaned up pollution quite a bit over the last couple of decades. And so we've gone from a situation where in a lot of our national parks, we used to have quite a bit of degradation of air quality and visibility in our parks. And we've made enormous strides in cleaning up the air quality in the United States so that we've moved from images that look like this to images that look like this. But clearly, these aerosols are affecting the visibility that we have anywhere we go. So let's go back to the climate piece, because that's a really, really important one. This is radiative forcing. So by that, we mean how much heating in terms of watts per square meter on the entire Earth from pre-industrial. So this is sort of, you could say, the human contribution to climate change. And there's two parts of this graph to look at. There's the size of the bar, and then there's the size of the error bar, which is the uncertainty. And for some of the well-mixed greenhouse gases, these are the things we hear about all the time: carbon dioxide, methane, nitrous oxide. These things absorb infrared light, and therefore they act as an insulating blanket. So the thermal infrared, the infrared that's irradiated by Earth, is blocked by carbon dioxide and by the other greenhouse gases, or absorbed, I should say, and then re-radiated back, so that these prevent loss of energy, light to space, and are a heating effect on the planet. Okay, so the CO2 effect all by itself is almost 2 watts per square meter. Now, what's a watt? Well, you know what a watt is in terms of its power unit, but think about it as a small Christmas tree light bulb. They're about this big, right? Now we have LEDs. We didn't used to have LEDs when we had incandescent bulbs. A little bulb like that might have been 1 or 2 watts on every square meter of the planet. That is the heating effect we are talking about. Okay. Now, there are also negative radiative forcing, and I showed you on the aerosols, there can be cooling effects. And so we can have clouds, like those ship tracks. They act to reflect more sunlight back to set base, so they would be a cooling effect. And then we can have scattering, like the Los Angeles picture, where aerosols are acting to scatter light back into space. And then we can have black carbon on snow. And so it's a very, very complicated story. But also in this is the the soot piece, which is an absorbing aerosol. So if you add all those up with all of those different parts, you get almost 2.5 watts per square meter. But now the error bars are much bigger, where most of those error bars are coming from these aerosols. So our understanding of the greenhouse gases, we understand those really well by comparison. But if you take this complicated picture and say, what is the net climate effect from aerosols? What do you want to believe? This one, or this one, or this one? Or don't forget the ship tracks, because the ship tracks are really important, because you've taken a blue ocean and turned it white. So from a climate point of view, suddenly it's a cooling effect. So it's a very complicated picture depending on which aerosols we're talking about. So an important part of that, as I mentioned, is this particular component, which we call black carbon. You can think of that as soot. And soot comes from diesel exhaust. It also comes from smoke plumes. And whether we're talking about the soot that comes directly from either a wildfire or diesel, or the soot that falls onto the snow and deposits, they're both positive radiating forces, that is, their warming effects. And then we have all these other ones that I mentioned in terms of the aerosols, aerosol clouds, and scattering. And so this is just a little bit more detail, specifically focusing on that black black carbon one or soot. So these are all giving us the components of the greenhouse effect. And to the best of our understanding, it's at least 2 watts per, I should say at least 1 watt per square meter, could be as much as 3 watts per square meter. And this is, so an interesting part of this, which is quite important for the greenhouse effect, is this one is increasing because CO2 is just marching up without any slowing. And these ones are probably going down because we're cleaning up our air pollution. So as we clean up our air pollution, then these ones are probably getting smaller, and then this one's getting more. And so the net radiative forcing is clearly going up. Let's look a little bit more. We'll get into the absorption or the interactions of aerosols with light. When we talk about aerosols, this is a complicated figure. You don't need to get too much out of it, but just that there's a couple of different size ranges. And so this is that particle diameter on the x-axis. And 2 microns is here. It should be 2.5, but anyway, this was earlier. There's different sources for the particles. If we're talking about really, really small particles, these are called Aitken nuclei or submicron particles, or sometimes we call them nanoparticles. Say this would be like 10 nanometers. So there's the micron, there's 10 nanometers. And these are come from gas to particle conversion. Ultimately, anything that starts out as a gas and ends up as a particle. So think about that soot that's coming out of a diesel engine. Truck going down the road, you see the black cloud of smoke coming out of it. How did that diesel form? Those diesel black carbon particles, well, it was gasoline or diesel exhaust, went into the engine, burned that diesel, small clusters of benzene-like aromatic compounds came out, they're really hot, they condense, and you get really fine particles in this Aitken nuclei or transient nuclei range that are like 10 nanometers. These things have Brownian motions, they collide into each other, they coagulate into this size range, and we get what's called the accumulation particles, which are between about 1/10 and about 1 micron in size. And these hang around for a little while. They don't go anywhere, meaning that they don't have any fast removals, so they accumulate. So you tend to get a bump in the size distribution. So most of the time when we're talking about our pollution, we are talking about particles that are in this size range. Now they do get removed eventually. They actually form clouds and they rain out. So cloud droplets will form onto these small particles and eventually they rain out. And that rain will carry with it whatever chemicals were associated with these. Now, the last hump in this thing we call a size distribution is the things that are mechanically generated, the bigger particles, 10 microns and above. Remember, the dust particles were up there. And these are anything that's mechanical, not hot vapor. So this could be windblown dust. This could be sea spray. Turns out the ocean makes particles going off in the distance, usually salt. Volcanoes can do it, and plant particles. So anything in this tends to have very different chemistry from anything down here. Okay, so we got a little bit of basics of the distinction between what we call the submicron aerosols and the coarse mode or super mode aerosols. That's sort of the most fundamental distinction. And remember, from a health point of view, these are the ones we can inhale deep into our lungs. So these are the ones we really want to be the most concerned with in terms of understanding their health impacts anyway. Well, then based on that, then the chemistry is different. And we don't need to spend a long time on this one, but just this is the figure isn't very good, but it's from an old study that actually one of the early ones to really show that the chemistry of these small particles and the big particles really follow the sources. And so just to go back to this, these ones tend to look more like pollution sources, and these ones typically had calcium, aluminum, iron, silicate, things that look more like dust. And so there's a difference chemically as well as the physical mechanisms that form them. Now we have more and more, we are getting more and more data on the chemistry of these aerosols around the world. There's some new instrumentation called an aerosol mass spectrometer. It's been around now almost 20 years, but um, wasn't around when I was a grad student. Well, when I was grad school, yeah, that's right. So these are kind of cool observations that tell us about the chemistry of the particles. And in these little pie charts, we have organic compounds, nitrates, sulfate compounds, and ammonium. And you can just get a sense of the differences of what kind of the chemistry we see in different parts of the world. So for example, in Asia, we tend to see more sulfur rich, usually US East Coast, and interestingly, Mexico City seem to see very high amounts of the organic fraction, as well as on the West Coast, very high fractions of the organics. And so you can get information about where these particles came from based on the chemistry as well. Let's get that one. Now, what do particles look like? We talk about nice, perfectly round spherical particles. Well, not so fast. When you actually collect particles and look at them in detail, they're not spheres at all. And so we often talk about our particles as if they were nice, idealized spheres, but that isn't a very good assumption. And so this is an example of electron microscope images of particles that were collected in London. And depending, you can look at these different ones, all of these, and this is the little bar here is 1 micron. So again, I was talking about submicron particles, and these are all combustion derived. And you can see that for the most part, the primary particle is well less than a micron, these little guys here. But a lot of times they cluster. And this, for instance, soot is well known to form these long chains. And so it becomes tricky to decide, is this a submicron particle or is this a 4 micron particle? Well, it's not really either. But then you look at this one, these particles tend to be larger, and you could see very regular structure that suggests a crystalline form. And that would then more likely be something like sea salt or dust. So these things, we're inhaling these into our bodies every single day. Okay. Obviously, if you live downtown or next to the freeway, you're inhaling more of them. If you live near some place that's very dusty, you're going to inhale more of the dust compounds. If you live near the ocean, you're going to inhale more of the sea salt. That's probably the least harmful of all of these. Okay, let's talk about light, because that turns out to be a really important piece of this. So a lot of different things can happen when a photon interacts with one of these particles. So I basically can define it in terms of scattering and absorption. That's how I would think about it. So in light scattering, photon comes in, interacts, and is re-emitted in some other direction, typically all directions, from the particle. And this is a physical process. The photon is not being absorbed. And it goes as lambda to the 4th, 1 over lambda to the 4th. So the wavelength to the 4th. And so longer wavelengths have longer wavelengths, less scattering, shorter wavelengths, more scattering, and this is Rayleigh scattering. And going back to, I think, Jen, you said that this explains scattering. Rayleigh scattering explains why the sky is blue, and this is actually the part of it that's scattering by gases. So this is Rayleigh scattering by the air molecules. In contrast, for aerosols, we have both scattering and absorption processes. And this is a figure showing total extinction. So that's the total loss of light. If you think of a Beer's law type expression as to what's causing a reduction of light at your location, we can have scattering, we can have absorption, we can have scattering by particles, and we can have absorption by particles. And so depending on the wavelength, this one is at 550 in the visible. Usually absorption is a relatively small part of the total, and the scattering by the fine particles is the most important part of light extinction. So if we go back to this picture, think about these, what's causing loss of photons between you and the image we're talking about is not absorption of those photons by the aerosols or by the gases, but scattering of the photons by aerosols. So scattering by the fine particles is the largest component of light extinction. Okay, so let's kind of briefly review the different kinds of aerosols that I'm going to talk about. Well, mostly I'll be talking about wildfire smoke. Dust, predominantly calcium, iron, silicon rich. We can have sulfur pollution, like from a coal plant or a smelter. We can have diesel exhaust, which is from, and I'll show a picture from diesel trains, which is predominantly organic and soot. We can have wildfire smoke, that's predominantly organic. We can have sea salt, that's predominantly sodium chloride. So all these different chemicals that give rise to different kinds of particles, and each of these has a different mix between scattering and absorption. So for example, diesel is known to be the most soot heavy of these, and so it has the largest component of black carbon or soot or elemental carbon, and it's the blackest of these, and so it's going to have the most significant signal in terms of absorption of light of all of these aerosol types. I've had the great fun to work at some of the most polluted places in the world. That's me, believe it or not. That's an old picture. Doing studies on pollution from one of the biggest pollution sources in the world in Russia. That picture was taken in about 1989. Okay. These we've looked at, so this sort of fits into that heavy industry. That was a smelter, copper nickel smelter in the Kola Peninsula. So those clouds of crud that we're seeing are probably sulfate rich metals that are coming from a very inefficient factory that's smelting ores and producing copper nickel. This is work we did. Oops, that figure got a little messed up. Work we did using a small airplane that we flew from Payne Field. I didn't fly it. We paid the pilots to fly it. Looking at pollution coming from Asia, arriving to the west coast of the United States. And that figure shows to see carbon monoxide, ozone, and particulate. So here are the peaks of particulate matter. These are lofts of pollution that came in from Asia, most likely coal burning in Asia that was transported across on the winds over to North America, something we've been very interested in and one of the reasons we started our work. So those pollutants were probably, again, heavy, a lot of sulfur, some soot, and other pollutants. This is work we did in the Columbia Gorge a few years ago with a group of students from UW-Bothell, where we're looking at coal pollution from the coal trains that run up and down the gorge. And we were interested in both the diesel components, the diesel burning, but in this particular picture, we had a camera that, motion activated camera. Every time a train went by, it would take a video of the train. And every once in a while, we'd see one of these coal trains that was losing coal dust as it went down the tracks. So this image here is showing us some of the pollution that's coming from coal dust that's blowing into the air as the train goes by at about 60 miles an hour, plus the diesel exhaust from the train as it went down the tracks. It was a pretty interesting project. And from that, we ended up publishing 2 papers on both the diesel particulate matter and the coal dust about these trains. And these were actually cited in the Washington State Environmental Impact Statement for a couple of projects. So that was kind of interesting work. And then lastly, wildfires. That has been a major area of emphasis for the last 8 years, I'd say, or 5 years. We have been seeing more and more smoke coming into Washington, or from our own fires, or from fires in British Columbia or California. Just last summer, the worst ever particulate concentration seen in Seattle, 264 microgram per cubic meter. And again, now you see why I'm showing you that picture from the Seattle Space Needle. Here's downtown on a nice clean day when the particulate matter was 4 micrograms per cubic meter. And on this day, 264 micrograms. Don't breathe. Hold your breath until it's gone is my advice. That is not healthy air. Why are we seeing so much smoke? It's just been a surge in the amount of wildfires burning over the last decade or so. And it really started around in the early 2000s. And there are lots of reasons. There's a number of fires that just get out of control, certainly related to how we've managed our forests, related to climate change, and also related to human ignitions. That's another talk, which I get asked to give a lot, but just kind of the big picture here is we are seeing more and more fires, and part of the story is climate change, but that's only part of the story. Those fires, it wasn't just Seattle, but I pulled out headlines from all over the place. These headlines are actually from 2018. This was before the worst year. So actually 2020 was even worse. But we've been seeing these really extreme smoke years in 2018 and then 2020 have been really bad. And we don't know what'll happen this year, but right now conditions are suggesting that we may in fact have another bad smoke year. So we'll see. It's hard to predict, but one of the important things, and I'll come back to the interaction with light, is we think of wildfire smoke as smoke, but it turns out there's a lot of different flavors of smoke. This is a picture I took. I was up on Lake Chelan in 2015, and the Wolverine fire had started. There was lightning up on that ridge that started this fire, and I took this picture. And interestingly, you can't see it in the picture. It was just taken with my cell phone. But there was actually just 1 or 2 trees underneath here that were burning, and these were actually flaming. And I could see with my eye the flames, but my camera didn't get it. But anyway, this was flaming combustion, and flaming combustion is known to produce a lot more black soot. And associated with that, you can see this black cloud that has a lot more elemental carbon in it. This part of the fire was smoldering, and you tend to see very different chemistry associated with that fire. And so the emissions depend on the combustion conditions. So generally, when we're talking about flaming combustion, we have lower things like hydrocarbons, more black carbon or soot, more nitrogen oxides, less ammonia, less primary particulate matter. And on the smoldering side, you see more particulate matter, and sort of the opposite of each of these. So less black carbon, less soot, and more primary PM per unit of fuel burned. That turns out to be a real interesting piece, because this is going to be important if we decide to do more prescribed burning. And actually, we are seeing prescribed burning happening more and more around the region. That means Forest Service going out there, setting fires on purpose to clear fuel to keep the forest in better shape, because fire is a natural thing. And so it turns out that this distinction here turns out to be very important in terms of how much particulate matter is getting released into the air by the different kinds of fires. Um, so yeah, I'll come back to that in just a second. So one of the ways tools we use to distinguish between these is something called the modified combustion efficiency. Think about it as how efficient you're burning your fuel. And so if you take a piece of wood, you burn it, and all you get is CO2, well, then you're burning it really efficiently. But if you're getting other things besides carbon dioxide, and carbon monoxide is what's used in the MCE equation, so the more carbon monoxide you have, the lower is your modified combustion efficiency. So if carbon dioxide is 0, then the MCE is 1. If the carbon monoxide is higher, then the MCE is lower. So for flaming conditions, we're going to say we have an MCE value higher, like 0.9 to 1. And for smoldering conditions, we'd say lower, maybe 0.9 or less. So this is just a distinction we can use. So if we have measurements of these two pollutants, then we can say, aha, that log or that smoke we're seeing was coming from a smoldering fire, that smoke we're seeing was coming from more flaming. And this is an example. So this is influence of modified combustion efficiency on PM enhancement from smoke plumes. This was data we collected up at Mount Bachelor in 2012-13, was published by one of my students, Nicole Wigder, in 2015. And so this is, you can think about more efficient combustion, less efficient combustion. So low MCE, more smoldering. And so this is a little bit tricky to interpret, but basically this is the scatter. And so this is the amount of PM per unit of carbon dioxide. So how much particulate matter in the air do we get per amount of CO2 for fuel that's coming from the fuel burn? So a higher value of this means more PM, and a lower value means less PM. And so this was kind of good data to show that if the worst way to burn your wood is to smolder it. And you probably know this from your own experience. You have a campfire and throw some water on it, it is making a huge amount of smoke as it sits there, and the combustion is very inefficient and smoldering. Whereas if the logs are burning and you can actually see the flames, you're getting a much more efficient combustion and less particulate matter. Aerosols are complicated, and these wildfire aerosols are super complicated because we have a couple of different processes going on, a whole bunch of different processes. So most of the smoke, if we go back to this picture, well, this picture is as good as any, probably 80 or 90% of that crud in the air, the actual particulate matter, is organic. It's not elemental carbon, but it's organic carbon. So organic compounds. Open your organic textbook, everything in there is in that smoke. You can find it all. And so I'm showing that with these brownish blobs here. And when it starts out, you have all these organic compounds, and they're relatively warm, and you can actually get loss of aerosol mass by evaporation. But then you have gases in the air, hydrocarbon gases. We call them volatile organic carbons, and they can oxidize and they can glom onto the thing and form what's called secondary organic aerosol. Well, okay, what if the particle is not organic, but it's one of those soot particles? We call them black carbon. Think elemental carbon. It's not pure carbon, but it's close. But these things can also get a coating of organic material. So this organic coating turns out to be very important for the radiative effects, the light scattering and light absorption effects. So as an example, two kinds of measurements that we do, we measure the aerosol scattering, and we do this with an instrument called a nephelometer. And the air is coming in here, aerosol inlet right there, actually. Whoops, make sure I can come back. Yeah, I closed up the inlet there. Okay, the air inlet is coming here, the air is going out here. There's a flash tube here, and that flash tube is flashing, boom, 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 broadband white light. and the detector is at 90 degrees. So for scattering, the analogy I make to my chemistry students is, imagine you're in a dark room and you take a laser and you shine it through the room. If there's nothing in the air, the laser makes it to the other side of the room and you just have a little bright dot on the wall and you can't see the path of the laser. But now imagine that you're in a smoky room and you can see the laser all the way across the room, because what you're seeing is the scattering effect from light that's being scattered off of the aerosol particles. And so this photomultiplier is measured at a 90-degree angle to the incident light here. And this is, so the nephelometer measures scattered light at 90 degrees. We can actually measure at different wavelengths. We can measure the scattering in different wavelengths. And what else? Oh, so the scattering coefficient is related to the Beer-Lambert law, like this. So we're able to measure this scattering coefficient. We calibrate it with a gas of known scattering, and we can measure these scattering coefficients, and they're very closely tied to how much PM is in the air, how much aerosols you have in the air. So this is measuring the scattering. We also measure the absorption of the light. And this is done, there's various ways to do it. The way we're doing it is we're using this instrument called a TAP, the tricolor absorption photometer. It's giving us absorption at 3 wavelengths, red, green, and blue. And this thing has a pump on it, and there's a little rotating valve here. And so it'll collect aerosol samples along the filter paper. And there should be 8 spots, as I remember. 1, 2, 3, 4, 5, 6, 7, 8. Yep. And it does a continuous measurement of light absorption through those spots at 3 different wavelengths, red, green, and blue. So you get a continuous measurement of the absorption of the aerosols. So we have both scattering and we have absorption. A couple of the equations that we apply: we can calculate the single scattering albedo. It's the ratio of how much scattering to the scattering plus the absorption. This is typically mostly dominated by the scattering, but absorption can also be big. And we also calculate this thing called the angstrom absorption exponent, absorption angstrom exponent, which tells us about the differential absorption at different wavelengths. If we're using 460 and 660, for instance, which are 2 of the wavelengths that we use. And so the point of the AAE is it's telling us something about this brown versus this black carbon. And going back to this, I intentionally show these organic aerosols as brown because they actually are brown. They really are. You tend to get smoke aerosols don't tend to be very black. They tend to be pretty brown because of that whole mass of organic compounds. And so for pure soot, these ratio tends to be around 1, but for wildfire smoke, we can get these AAE values up to about 4. And what's happening is we're getting a lot more absorption at the shorter wavelengths because of chromophores in the organic compounds. So this is a picture of data. I actually just pulled this off of our site of our website for Mount Bachelor for today. And these are both green, so somewhere around 550 or so nanometers. The nephelometer and the TAP, so for scattering and absorption, they're at slightly different wavelengths, which is a little bit of a pain. I can't remember that one's at 532 and one's at 550, I think. But just this week, we had several pretty significant aerosol events on the top of our mountain, right at 9,000 feet. We had one on May 5th, whatever day that was, and we had another on May 6th. This is in Greenwich Mean Time, by the way. And then we had this one. And if you look at these two, the absorption to the scattering looks pretty similar. You know, this peak's the biggest, and well, the broad peak here. And these two were associated with fires. Now, it's only May. Why are we getting smoke already in May? Anybody want to guess?
Lightning strikes?
Nope.
No.
I'll give you a clue. These are not natural fires. These are prescribed fires. So what's happening in various spots around the Pacific Northwest in the springtime is more and more land managers are setting fires to reduce the undergrowth and the brush in forests that haven't burned in 50 years. Why are they doing it in May? It's raining today. Well, that's half the point. They don't want to do it in August, right? Because if one of these fires gets loose and they just burn half the state down, they are in big trouble. So they're doing it in the shoulder season when it's dry enough to have a fire, but not so dry as to get completely out of control. And I just grabbed a air quality and which has satellite maps overlaid on it. And this is actually the one for yesterday. And these are, I'm pretty sure these are all prescribed fires. And this one has the plume showing the plume, and this one coming from a fire in Southern Oregon, going right over our research station at Mount Bachelor, which would be right about here. So those ones are some kind of a fire. I'm pretty sure they're prescribed, but I'm not 100% sure. This is a really interesting one. And here's a big peak of absorption, but only a little peak scattering. Means that whatever aerosol that came here was very, very black, much blacker than this one. Because this one, you can see what the ratio of scattering to absorption was, whereas here, the ratio of absorption to scattering was much higher. So this was a really black aerosol. And I just a few hours ago confirmed with the ski area, they are still operating and they're still doing grooming on the mountain. And because this is Greenwich Mean Time, this one turned out to be right around 7 Greenwich Mean Time. And we're 7 hours from Greenwich Mean. So this was midnight on May 5th. And so it was midnight between the 5th and the 6th local time. It turns out, I confirmed with the ski area that they were running their diesel groomers around the mountain that night. And one of them must have gone right up the summit and parked. And that one really looks like diesel because it's so much blacker than the other ones. So, and I think that's pretty much what that is. I don't know how much, well, let's see what our time is here. 12. Oh, okay, I'm gonna skip over this one. If you're really interested, we can talk more about the wavelength dependence of the light, but I'll just show this one. This is an example of using some of those equations. This is in a paper by one of my postdocs using data from Mount Bachelor. Difference in, this is scattering to carbon monoxide. So this is how much particulate is formed. This is that single scattering albedo, how black is the aerosol. And this is that angstrom absorption exponent, which is telling us how different the absorption is at different wavelengths. And these were regional biomass burning events, regional fires versus long-range transported fires. And we see sometimes smoke coming all the way over from Siberia. And there were very clearly differences in the radiative properties of these aerosols. So this is a new work by a colleague of mine, and I'm not showing the detail, but just wanted to show a kind of an idea of the conceptual idea of these aerosols. They start out, there's a lot of differences how they start out and how they change over time as they age. And going back to the climate piece turns out to be very important in terms of the climate effects. So let me just get to a summary and leave some time, hopefully, if there's some questions. So studying the global environment, it's a highly interdisciplinary process. Clearly, physics and chemistry both needed to understand the human impacts on the atmosphere, but we also need biology. We also need ecology. We also need statistics. We also need medical expertise to understand the impacts on biological systems. And there, I'm thinking us, right? I mean, I do have to talk to health people so we can say, hey, what are the impacts of this stuff that we're breathing? And from, my interest and what I call the key areas then is air pollution and health and global warming. And global warming is a problem that's going to be with us for a long time, and certainly one year we'll be hearing more and more about it. And it's going to become, the major challenge, one of the major challenges of our time, of this century, is how to address the fact that the planet is getting warmer. What do we do about it? What are the predictions for the future? So with that, if there's any questions, I would be happy to take them.
Dr. Jaffe, I had a real quick question. So on one of the very first slides, you kind of showed all the different areas of around the world that you've taken measurements from. It appeared like everything was in the northern hemisphere, and I didn't know if that was just coincidental or if there was a reason for that.
That is true. Well, it's not that I set out to study pollution all over the planet. I didn't set out to do that. It's sort of anecdotal, almost. Like, I got my PhD at the University of Washington, Seattle. I took my first faculty job at the University of Alaska. So I studied, that's why I started out studying pollution in the Arctic and things in Alaska. And that's why some of these, like this is in Svalbard, where we did measurements in Alaska. We want to do similar measurements in Svalbard. And we also did measurements of that smelter, that heavy pollution source in the Kola Peninsula, which is that dot. And then when I moved and took the faculty job at the University of Washington at UW-Bothell 20 years ago, was the first scientist hired here, actually. Obviously, one of my goals was actually to shift towards looking at Pacific pollution in the Pacific. And we were one of the first ones to discover, that we could see pollution coming from China over to the United States. And that sort of led us to a bunch of collaborations in Asia. And so we did measurements at this station, and this is an island it's a Japanese island, and that they have an atmospheric research station that we did measurements there. We did measurements in Korea. And then lately I've had collaborations in China where we've actually done measurements collaboratively with scientists in China. So, sort of all of those dots were sort of all associated with the fact that I got my first faculty job at Alaska and I got my second faculty job at UW. Beyond that, the others are just kind of random dots. These guys needed an instrument that I had to do an experiment out here. We were interested in mercury for a long time, and we did a lot of work on mercury, and that experiment was based in the coal power plant region of the United States. I did a sabbatical year in Italy, so we had to do some measurements there. So kind of the explanation.
I think there was someone who asked a question in the chat. They asked if there were any similar the facility that you have on Mount Bachelor. They were asking if there were any similar facilities on the East Coast, or if the age and therefore the height or the altitude of the mountains prevented that.
Yeah, well, yeah, on the West Coast we have mountains that they don't have in the East, but that said, there are some mountains. There's a site that measures pollution on Mount Washington. It's about 6,000 feet, and they see a lot of pollution coming out of the East Coast. There's a site in New York at Whiteface Mountain. So there's many different levels of these research networks. The EPA and the states operate a routine monitoring network where they're focused on ensuring that the air we breathe is clean, or monitoring how good the air is where people live. So there's a very extensive network of measurements of particulate matter, carbon monoxide, ozone, nitrogen oxides across the country. But take particulate matter. The EPA only measures one thing, PM 2.5, the mass of particles smaller than 2.5 microns. They don't care about the chemistry. They don't care about its climate effects. They don't care about its absorption or its scattering. So this is a monitoring network. Now, on top of that, NOAA has a few stations. They have a small number of stations, like 4. And they have none on the West Coast now. They used to, but they don't. We actually collaborate with NOAA, and we take some measurements for NOAA. As far as sort of a university operated research station, I didn't show the pictures, but we've had, um, I've had $500,000 instruments go up and down that chairlift. Some ours and some from other universities. I've collaborated with probably a dozen different universities to make measurements there. So we've done some really high level measurements at the summit of that mountain that, haven't been done elsewhere because we have a unique environment where you're sampling sort of unusual air. So there's not too many university run research stations like this in the country. Let's say there's 3 or 4. The University of California has one. State University of New York has one. University of Utah has a mountain site in Steamboat Springs, Colorado, and then we have ours here. And so, we talk to each other and try to make sure our data are comparable.
Sure. I mean, kind of dovetailing on that a little bit, for those of us who study astronomy, there are quite a few global collaborations. There's the LSC, there's Nanograv, there's handfuls of others. With the increased focus on climate change, are there any large-scale global collaborations that are attempting to tackle that right now? That maybe there are research opportunities for students.
Well, there are. There definitely are global collaborations on both greenhouse gases and aerosols, and the focus for that work is probably NOAA, the National Oceanographic and Air Administration. And so NOAA has a national U.S. network of stations where they measure greenhouse gases, and we are part of that network. And if you go to the NOAA network, you'll find us on that map because we measure carbon dioxide for them. And so they use our data as part of they actually use it in models to help understand how much carbon dioxide we're generating versus how much is coming from other countries. And then NOAA collaborates with, sort of is the focus of collaboration of greenhouse gas measurements with other countries. But there's also many different research collaborations as well. Now, NASA's playing a bigger and bigger role. There's a lot of these things we can see from space. I didn't talk so much about NASA satellites, but if we go to, well, I didn't talk about them at all, but if we go to this picture, what I'm showing, whoops, you can't, you still see it?
Mm-hmm.
Yeah, so these are actually satellite-derived smoke plumes that are generated. These are actually generated from NASA satellite data, but the maps are generated by NOAA employees. So clearly there's a lot of overlap. And then people like me use them to oh, look there's a smoke plume out there today. But there's also a lot of satellite products that are giving us aerosols, giving us carbon monoxide, giving us nitrogen dioxide measurements. So we're doing spectroscopy from space by looking at the reflected light that's coming from the sun, reflected back to the detectors that are on board that satellite, and you get absorption features. Now, it's a complicated problem to deconvolute how much is in the atmosphere because that photon traveled a weird path. It didn't travel straight through the atmosphere. It took a slant path, and you may have clouds, and there can be absorption all along the path, and it's a very tricky radiative transfer problem figuring that out, but they do it. So there are a lot of different kinds of collaborations like that.
Nice. Thank you.
And honestly, I got into this as a chemist. I took lots of physics. I kid when I say, I hadn't taken physics in 30 years, which is true. I haven't sat in a physics class except to see some of our physics professors teaching once in a while, but I haven't taken it as a student in a long time. But, I got into it as a chemist. And when I started out in chemistry, I wanted to measure the chemical composition of things. It was, I could easily have gone the physics route and be looking at satellite data to look at the same kinds of things, but looking at spectroscopic data from space, that is a big, big field now and a very important one, because unlike what we can do, we can understand everything that's in that molecule of air on the top of our mountain, but we don't know what's going on 10 miles down the road. Whereas from a satellite, you can see, near global coverage every day.
Nice. looks like another question just popped up here from Jen. How useful would air chemistry research stations, hold on, air chemistry research stations on astronomical observatory mountains like Cerro Tololo or Kea be?
Yeah. Well, I'm sure that would be useful. I mean, funding is always our challenge, right? So Mauna Kea is in Hawaii, right? So you should know that NOAA operates one of its flagship stations is on Mauna Loa. So they have one of the high elevation sites that's at 14,000 feet on Mauna Loa. And that station has been operating, boy, I want to say 50 years. And that was actually one of the first stations to document the global increase in carbon dioxide, the sort of the large scale increase in carbon dioxide, worked by David Keeling many decades ago. I believe it's the Japanese or the Koreans, I can't remember, started a station up on Mount Everest, not on the summit of Mount Everest, but at about 15,000 feet, I want to say. So I don't know if it's still running. I'm sure it's very hard to maintain. So, these stations are very valuable. The challenge is keeping them going. So if there is already an astronomical observatory, that can be a very powerful foot in the door, so to speak, since the infrastructure is already there. I will say, half of our problems are things like dealing with heat and dealing with HVAC and temperature control and getting the data down and just sort of basic things that are part of any kind of scientific enterprise. We spend a lot of time on just because we run the station. I wish we didn't run the station. I wish somebody else ran it. Keep the lights on.
Nice. Any other questions out there? Anybody else? So going once. Going twice. All right, we'll go ahead and call it. Yeah. Well, Dr. Jaffe, again, thank you so much. I really appreciate you taking the time to hang out with us and share your expertise.
Okay. Thank you so much.
Absolutely.
All right. Take care.
Yep.
Bye.
You too. For everybody else, thanks so much for joining. I really appreciate you guys hanging out. Next week, I believe we have one of our own club members who's going to be doing a presentation. I'm actually not really sure what he's going to be presenting on yet, but he is somewhat of a mad scientist, so I'm sure it'll be quite interesting. Thank you very much for being here. Really appreciate it. And again, this session will be posted up on our YouTube channel, which Jen, if you want to throw your contact info in the chat, I can provide you with that YouTube channel if you want to revert back to anything that Dr. Jaffe has said in his presentation. But other than that, I don't have any business to speak of. So we can go ahead and call it. I know the meeting ran a little bit longer than normal. But again, thanks so much. Really appreciate it. And I hope everyone has a great weekend.
Deal.
All right, later. All right, thanks, Jen. I'll shoot you an email.
Excellent. Thank you for having me.
Yeah, absolutely. Thanks for joining us today.
Hey, Nate, by the way, at some point we should send out an announcement about the SPS induction ceremony and club awards to the general student body.
Okay, cool. Yeah.
Like I guess the general physics body.
Yeah. What I mean, aside from date and time, what do you think we should include in that email? Do we have I mean, I know that Dr. Key has a list of like people who are eligible, but do we have a list of people who are actually planning to be inducted?
I don't know, but we should also, because it is just club awards as well, we should invite just
The entire club body? Sure.
Yeah,
Okay.
or like the entire physics body too, right?
Oh, yeah,
That
yeah.
and that can be done through the UW physics Canvas page,
Okay, cool,
because
cool.
there should be almost everyone in there.
Okay,
But
nice.
that's a good thing. And then also, once we decide on awards, which we should probably do pretty soon, we should email the people that are getting an award that they are doing that, so that they can actually show up.
That is a good call. So
Like, we don't have to tell them what they're getting, but
totally. So yeah, I spoke with Court yesterday. We had our little planning session. We kind of flushed out some other ideas and just kind of how to get the entire event planned. And we came up with a variety of different awards. You know, some had been suggestions from previous meetings. And we were hoping to have that kind of be the focus of our next officer meeting, like really getting that lined up. But I'm wondering if maybe we need to try and do that a little bit sooner, because that only gives us a few days to alert those people.
what we could do is we could ask the officers if they'd be okay with meeting this Monday.
This Monday. I think that's a good idea. Yeah,
'Cause, I
would you
mean,
mind?
people show up anyway, or people ask if it's this this week anyway. So
Yeah.
I do that a lot, so I don't blame them.
Would you mind throwing a quick a message out on the officer channel, see if people are open to doing that, and then we can try and plan on that, and just again let everyone know we're trying to solidify up the awards, and then we can also go over just kind of the itinerary that Court and I drew up. Yeah. Okay. Anything else?
Nope.
Okay, cool. All right, well, I'm gonna jump off here. I've needed to pee for like the past 35 minutes, so.
I don't blame you.
All right, well, I'll talk to you later. You have a great weekend, man.
You too.
Bye.